Buffers play an important role in a variety of natural and biological systems because of their ability to resist changes in pH. As a consequence, the pH of the system stays approximately constant even after the addition of small amounts of strong acid and strong base. Buffers are composed of a weak acid and its conjugate base, which usually occurs as a salt, or a weak base and its conjugate acid, which usually occurs as a salt as well, as shown here. Now, in order for a buffer to be effective, there must be approximately equal concentrations of the conjugate acid-base pairs present. And by this we mean they must be within a factor of 10 of each other. Examples of buffer solutions that contain a weak acid and its conjugate base are hydrofluoric acid and fluoride, hydrocyanic acid and cyanide, and acetic acid and acetate. And examples of buffers that contain a weak base and its conjugate acid are ammonia and the ammonium ion. A buffer solution can be prepared by mixing either a weak acid with a salt of its conjugate base, whereby the salt will dissociate to produce the conjugate base of interest, as shown here, or a weak base with the salt of its conjugate acid, where the weak base dissociates to produce the conjugate acid of interest, as shown here. In the next step, the buffer solution is adjusted to the desired pH through the addition of either strong base or strong acid. If strong base is added to the buffer solution, then the strong base will neutralize some of the weak acid, thereby increasing the pH. By contrast, if strong acid is added to the buffer, then the strong acid will neutralize some of the weak base, thereby decreasing the pH of the buffer. The pH of buffer solutions can be easily calculated using the well-known Henderson-Hasselbalch equation, as shown here. Briefly, it tells us that the pH of a buffer equals the pKa of the acid form plus log of the concentration of the base divided by log of the concentration of the acid, where the acid and base are conjugate acid-base pairs. So, for a weak acid buffer system, using the equilibrium shown here, we see that pH is defined as the pKa plus log of the concentration of A minus divided by the concentration of HA. For weak base buffer systems, using the equation shown here, we see that the pH is defined in the same way, where the pH equals the pKa of the acid form plus log of B, which is the base, divided by BH plus, which is its conjugate acid. In a buffer, the buffer components neutralize small amounts of strong base or strong acid by shifting the position of the equilibrium. So if we take a look at a buffer consisting of a weak acid and its conjugate base, we see that we can set up an equilibrium reaction between the two components, where the weak acid plus water will exist in equilibrium with its dissociation products, H3O+, and its conjugate base, A-. So, if we have this buffer system and we add a small amount of hydroxide, we'll see that the hydroxide reacts with the weak acid to form A-, as shown in this equation. And so as a consequence, the concentration of A- increases and the concentration of HA decreases a bit as it is consumed. By contrast, when we add a small amount of strong acid to our buffer, such as H3O+, we see that the H3O+ reacts with A-. And as a consequence, the weak acid HA is produced. So the concentration of HA increases, and there's a small decrease in the concentration of A-. Here we'll see what actually happens when a strong base, hydroxide, is added to a buffer. As you may recall, a buffer is composed of a weak acid and its conjugate base, or equivalently, a weak base and its conjugate acid. So here we see the equilibrium reaction between the weak acid and its conjugate base. And we see that our weak acid HA reacts with water, and we have an equilibrium reaction that produces H3O+ and its conjugate base A-. Next, if we add our strong base to the system, we see that our strong base dissociates completely to produce hydroxide. And it's this hydroxide that reacts with our weak acid. So the reaction we have is between our weak acid and the added strong base. So here we have our weak acid plus our strong base. This reaction will go to completion because it's a strong base. And in this process, the weak acid will donate a proton to hydroxide. And this produces our conjugate base, A minus, plus water. So this is our neutralization reaction. So to see what's actually going on, we'll look at the ICF table. And if we start with the same concentration of HA and A minus, and we add a small amount of our strong base, hydroxide, we see here that hydroxide is the limiting reactant. And so the amount of hydroxide determines the change in the number of moles. And so here we see that the change of weak acid is minus 0.3 moles, and the change of hydroxide is minus 0.3 moles, and the change in its conjugate base is plus 0.3 moles. And adding these up, we see that the final concentration of our weak acid is 0.7 moles. We've consumed all of the hydroxide, so the buffer has consumed all of the hydroxide that we added, and we're left with 1.3 moles of the conjugate base A minus. And as you see, the concentration or the number of moles of our weak acid went down, whereas the number of moles of the conjugate base went up. You can see here that we still have our weak acid and the conjugate base, and so we still have a buffer. And so we can find the pH of the system using the Henderson-Hasselbalch equation, which is simply the pH equals the pKa plus the log of the weak acid divided by the concentration of its conjugate base. Here we'll see what happens when a strong acid is added to a buffer. Here we see the equilibrium reaction between the buffer components, and in this case we have our weak acid plus water exists in equilibrium with H0 plus and its conjugate base A minus. Now if we add a strong acid to this buffer system, we see that the strong acid will go to completion and produce H0 plus. Okay. And so it's this H0 plus that will then react with the conjugate base A minus. And this is the basis for the neutralization reaction. So we have A minus plus H0 plus. Here recall that H0 plus is a strong acid, and so it will donate a proton to the weak base A minus. And since H0 plus is a strong acid, this reaction goes to completion, and so we produce HA, which is the conjugate acid, plus water. So this is our neutralization reaction. And if we want to see what's actually going on in this neutralization reaction, we'll look at our ICF table. And if we happen to start with equal concentrations or equal number of moles of the weak base and its conjugate acid, and we add a small amount of strong acid, we see here that the strong acid is the limiting reactant, and so this will determine the change in the number of moles. On the reactant side, the change will be negative, and on the product side, the change will be positive. Next, we simply add up the columns, which gives us 0.7 moles of our weak base A minus remaining. We end up with no strong acid because all of our strong acid is consumed by the buffer. And we end up with 1.3 moles of our conjugate acid, HA. And as you see, the number of moles of A minus went down and the number of moles of our conjugate acid went up. Now here we'll see that at the end of this reaction we have a weak base and its conjugate acid. And so we still have a buffer. And again, we can find the pH of this buffer using the Henderson-Hasselbalch equation, which is pH equals pKa plus log of the concentration of the weak acid, or weak base, divided by the concentration of the weak acid. Here we see how a buffer actually works. For a weak base, we can see that we have an equilibrium reaction with a weak base and water, which will exist in equilibrium with its conjugate acid, pH plus, and hydroxide. If hydroxide is added to our buffer system, then we can see that the hydroxide will react with BH plus, consuming BH plus, and producing the weak base B. And so we see that the concentration of B increases and the concentration of BH plus decreases. However, we still have appreciable quantities of weak base and its conjugate acid, and we still have a buffer system. If we take the same system, however, instead of hydroxide, we add H3O+, we see that the H3O+ will react with the weak base, B. Here, a proton will be donated to the weak base, producing BH+ and water. And so we can see that the concentration of BH+ increases, whereas the concentration of B decreases. However, once again, we still have appreciable quantities of weak base and its conjugate acid, and therefore we still have a buffer. This is a slightly different way of looking at exactly the same thing. Here we have our buffer system where we have significant quantities of weak base and its conjugate acid, so we have a buffer. If we add strong base to the system, the strong base will dissociate to produce hydroxide, and the hydroxide will react with BH+, the conjugate acid, and so the reaction will be between BH+ and hydroxide. Here, the weak acid will donate a proton to hydroxide, producing a weak base B and water. And this is our neutralization reaction. And if we take a look at an ICF table, where we have the initial number of moles of weak acid and hydroxide and conjugate base, we see that the change in the concentration will be determined by the limiting reactant, which in this case is hydroxide, and so all of the hydroxide will be consumed. And therefore, the number of millimoles of weak acid, BH+, will decrease, and the number of millimoles of B, or weak base, will increase. However, we still have significant quantities of both weak base and its conjugate acid, and therefore we still have a buffer system, and therefore we can determine the pH with the Henderson-Hasselbalch equation. Similarly, if we take the same buffer system, but in this case we add strong acid, our strong acid will react with water to produce H3O+, and this H3O+ will react with the weak base. And the reaction will look like this. Here, H3O+ will donate a proton to the weak base, and the weak base will therefore gain a proton, so it will gain a hydrogen and gain a charge of +1, whereas the H3O+ will lose a proton and lose a charge of +1 to produce water. If we look at the ICF table for this reaction, and if we take an example, we start with 1 mole of weak base, 1 mole of its conjugate acid, and we add 0.3 moles of strong acid. We see that the strong acid will be the limiting reactant, and the change will be minus 0.3. And adding the columns, we see that the number of moles of weak base will decrease to 0.7 from 1, and the number of moles of its conjugate acid will increase from 1 to 1.3. However, once again, we still have appreciable quantities of the weak base and its conjugate acid, and therefore we still have a buffer system. And once again, we can solve the pH from the Henderson-Hasselbalch equation, as shown here.